How do you conduct a hypothesis test? How do you decide if you have convincing evidence of a statistically significant result? To answer these questions, we're going to do number 4 from 2018 AP Statistics Free Response Questions. Please subscribe to my channel and let's have some fun. You do the math. Here's the problem we're going to attempt, so pause this frame and make sure you read the entire problem. Part A says, based on the design of the study, would a statistically significant result allow the medical center to conclude that the new procedure causes a reduction in recovery time? So this is asking about cause and effect. Now, here's my answer. I'm going to read this and then I'm going to explain in a little more detail. The answer is yes. A statistically significant result would allow us to conclude the new procedure causes a reduction in recovery time, since participants were randomly assigned to either the standard or new procedure. So it's the random assignment within an experiment that allows you to infer cause and effect if the result is statistically significant. So a statistically significant result from a randomized, controlled, comparative experiment with sufficient replication is a source of convincing evidence of causation. If you'd like to read more about what makes an experiment well designed, check out my video on experimental design. All right, Part B actually wants us to do a little bit more work. They provide some summary statistics, and they ask us if the data provide convincing statistical evidence that those who receive the new procedure will have less recovery time. So this is going to be a hypothesis test or significance test for the difference in two means. So I'm going to follow the state plan, do, conclude system of creating a confidence interval or conducting a hypothesis test. So this procedure, this process will work for either creating an interval or a significance test. So the first part is state. I'm going to define my parameters. And remember what a parameter is. It's a measurement describing a characteristic of a population. So here I'm going to define mu. Don't define x bar. That's not a parameter. That's a statistic. I'm going to define mu s as the mean recovery time for all patients similar to those in the study assigned to the standard procedure. So mu s stands for standard procedure. And notice that I'm saying that it's the mean. Don't just say mu s equals recovery time or something. You have to define the parameter as either a mean or a proportion or some other description of the population. I'm also going to define mu n as the mean recovery time for all patients similar to those in the study assigned to the new procedure. Notice how specific I'm being in my definitions. I'm also going to state my hypotheses. There's two ways to do that when you're comparing two independent samples. You could either say mu s is equal to mu n, or you could say the difference is equal to 0. All right, the next phase is plan. This is where I check the conditions. So there are typically 3 conditions for inference. The first one is random sampling or random assignment within an experiment. Since this was an experiment, I'm going to say that participants were randomly assigned to the standard or the new procedure. The second condition, now I put a little asterisk after this. The second condition is usually the 10% condition, which says that the sample size is small enough relative to the population to mimic the effect of independent sampling. Usually sampling is without replacement. So it's not truly independent. But if the sample size is small relative to a large population, it's close enough that it doesn't actually affect the accuracy of the answer. Now, within the context of an experiment, you don't need to check this condition. I just put it here because I almost always check the 10% condition, and I don't think there's any harm in saying that the 110 participants in the study are fewer than 10% of those potentially able to receive the standard procedure, and a similar statement for the 100 in the new procedure group. The third condition, which is necessary, is the normality assumption. So we can assume a normal sampling distribution because of the central limit theorem. Now, this one works for means. For proportions, you have to check the large counts condition. So since both samples here are greater than 30, the central limit theorem is met for both samples, so we can assume a normal sampling distribution. This is basically permission to do the next step, to use the formula we're about to use, which is based on a t-distribution, which is a normal distribution. Next comes the do phase, and I'm going to do this both with the formula and then with technology. You don't have to do it both ways. You choose one way to do it, and you do it that way. So with the formula, if you go to the reference table, here's what you're given. So you get this very general, generic format which is the standardized test statistic, which is either a z or a t, or could be a chi-square, is equal to statistic minus parameter divided by the standard error of the statistic. So you have to kind of understand in the context of your problem, what's the statistic, what's the parameter, and what is the standard error. The standard error you can look up also. So if you go further down the reference table, you'll find this. Okay, so this is for means. And we have two populations here, right? We have the standard procedure patients and the new procedure patients. So we're using that second one, that bottom row there, for two populations, x bar 1 minus x bar 2. And the standard error of the sample statistic is the square root of standard deviation squared over sample size plus the other standard deviation squared divided by sample size. So we have all that information. So that's going to be the denominator. The statistic is going to be the difference in the sample means. Statistic comes from a sample. And the parameter is going to be the difference in the population means, which are mu. So what I did was I wrote out the specific formula that I'm going to use here. We're using a t-score since this is a hypothesis test for the difference of two means. And when you're dealing with means, intervals or tests, you're going to use t unless you're in that rare case where you know sigma, the population standard deviation. That's really rare. We don't know that here. So we're using the t distribution. You use z for proportions. Okay, so t equals statistic minus parameter divided by standard error of the statistic. So I plugged in all the pieces. I put all the pieces together to get my specific formula that I'm going to plug into. So x bar minus x bar is 217 minus 186. I'm subtracting 0 because that's the difference from the null hypothesis. Remember, the null hypothesis was that the difference was 0. Then I'm going to divide by the standard error with those numbers that I was given plugged in, 34 and 29 for the standard deviations, and then 110 and 100 for the sample sizes. And if I type that into a calculator, I get 7.127 as my t. Next, I draw a normal distribution, and I want to find the shaded area to the right. Now, how do I know to shade to the right? Well, I know because the alternative hypothesis was greater than. Right? So if you have a greater than alternative hypothesis, you shade to the right. If your alternative is less than, you shade to the left. And if your alternative is not equal to, you have a two-tailed hypothesis, which means you have to shade to the right and the left, which basically means find one tail area and double it. So to find the shaded area here, I'm going to go to TCDF, which is like normal CDF, but it's TCDF for the T distribution. And the additional piece of info that they need is the degrees of freedom. So you go to second vars TCDF. You type in the left end point of the shaded region, which is 7.127. This is where a picture comes in handy. The right end point, which is infinity. So I type in 1e99, which means 1 times 10 to the 99th power. The e is second comma. And then degrees of freedom. Now, when you have two populations and two samples here, you're going to use the smaller of the two samples minus 1. So 100 minus 1 is 99. If you type all that in, you get the p-value of 8.43 times 10 to the negative 11th. So this is way less than 5%, way less than 1%. Now let's do with the calculator. All right. So on the AP, what you have to write down is either the formula or the name of the test that we're doing. So the name of the test we're doing is a two-sample t-test for the difference in means. And when you go to the calculator, this is called two-samp t-test. Where you find this is stat tests. Scroll down until you find two-samp t-test. If you have the raw data, the original data, you could type that into L1 and L2. But we have the summary statistics. So we're going to click on stats, and then we're going to enter X bar 1, S1, N1. So the info for the first sample, then the info for the second sample. And really, really important, you have to highlight the alternative hypothesis. Okay, so that's second to last line right above pooled. Mu1 is greater than mu2. You can't see it on this slide here, but I highlighted greater than mu2. And I hit enter to select it. Never pool. The only time you would pool the samples is if you knew that the standard deviations were equal in the two populations. But we were not given that. We have no reason to believe that. And you hit enter, and here's what you get. You get a t-score of 7.127. That's exactly what we got when we did it by hand. We get an even smaller p-value here. We get 8.358 times 10 to the negative 12. So this is definitely a significant result. Now, why did we get a different p-value? Well, it's because the way the calculator calculates degrees of freedom, as you can see, they have 207.179. They use a much more complex formula to calculate degrees of freedom when you have two independent independent samples. But for our purposes, we come to the same conclusion. So on the AP, they would accept either answer. So now it's time to conclude. We have to write a sentence. So here's my sentence. Since the p-value equals 8.358 times 10 to the negative 12, I used the calculator one, but you could use the one that we got with the formula, is less than 0.05 or less than 0.01, whatever significance level you choose, we reject the null hypothesis. So the first part of my sentence is always a decision with respect to the null. Do you reject the null or do you fail to reject the null? And why? What was the p-value? The second part is the context. We have convincing evidence the mean recovery time of patients receiving the new procedure will be less than the mean recovery time of patients receiving the standard procedure. So make sure you have two parts. Since the p-value equals whatever, we reject or we fail to reject the null hypothesis. And then new sentence, we have convincing evidence or we do not have convincing evidence of the alternative hypothesis stated in words in context. And that's how you conduct a hypothesis test for the difference in two means. I hope you had as much fun as I did. Please subscribe to my channel, and as always, may the math be with you.